I'm going to be introducing Hüseyin Böler. He's a PhD candidate. When did you become a candidate, by the way?
Like 2012.
2000, no. Did you pass the exam?
Did you 2013, I guess.
Did you pass the prelim?
Not yet.
When you pass the prelim, you become a candidate.
I guess it is up to
You are a PhD student.
Okay, I'm a PhD student.
All right. Today he's going to talk about the field investigation of railroad bridge approach tracks substructure behavior. If you already don't know Hüseyin, just a brief introduction for him. He graduated from Atatürk University in Turkey. It's one of the colder places in Turkey, northern eastern part of Turkey, in 2008. He later obtained his MS degree from the University of Illinois at Urbana-Champaign. He's currently a PhD student and working with Professor Tutun there. Let's give him a round of applause and start his presentation.
Thank you. So today I'd like to talk about a common problem that railroad struggles with, bridge approach problem. It is one of the track transition problems. It is classified as track transition problem. And to display the outline for today's presentation, I will give a brief introduction to the project. I will give later on transient deformation behavior, which is the displacement time history we measure. I will display computing acceleration computation using displacement time histories, analysis of those accelerations, and the remedial measures we apply to attenuate the problem, bridge approach problem, and later I will give the conclusions. This project was funded by Federal Railroad Administration. The official project name is Mitigation of Differential Movement at Railway Transition for U.S. High-Speed Passenger Rail and Joint Passenger/Freight Corridors. Principal investigator was my advisor, Errol Tutumler, and co-PI was the Professor Stark. There were two research engineers, and there were one research engineer, Debakanda Mishra, and visiting research scholar, Jim Heisley. The project duration, it took 51 months from October 2011 to December 2015. The scope of the project was monitoring railway transition and identifying the common problem in bridge approaches, as well as numerical modeling of those numerical modeling of railway transitions. The project took place was AMTRAK Northeast Corridor. It is a section of railroad track which is 457 miles. It has around 17 tunnels and around 1,200 bridges. Daily, there are 2,200 passengers riding on those corridor, and you can see the other details regarding that part of the track. We have chosen 3 bridge locations on Chester, Pennsylvania. Those are Madison Street, Upland Street, and Colvest Street location. For Madison Street location and Upland Street location, we have chosen 2 sub-locations. One was 12 feet away from bridge in Madison Street location. For Upland Street location, the first sub-location was 15 feet away from the bridge. And the second sub-location was 60 feet away from bridge for these both locations. The first choice, for example, for Madison Street, for 12 feet, we call that near bridge location, and the 60 feet location we call open track location. In terms of Caldwell Street, the location we have instrumented was 80 feet away from bridge, and this was a control location. And in this location, we have actually instrumented both ends of the tie. In spite of we only instrumented one end of the tie in Madison and Upland Street locations. Those are the instrumentation we have used. The first one was multi-deflectometers, MDDs. I'm not going to go into detail that how they work, but briefly, what they do, we divide ground in 5 layers, and we anchor the MDD is at 10 feet from ground, like around 3 meters. And the other important thing in here is we installed the first MDDs in the tie. So for layer 1 deformations, we actually obtain whatever the movement of the tie. So if there is a gap underneath the tie, we also include that in our deformation time history. The other instrumentation we have used is strain gauges. We have installed those on the neutral axis of rail. What they do is basically as wheel passes through, this rail bends. By using bending strain, they transform those to vertical displacement. Then later they calculate the loads and give us the dynamic wheel loads on the specific location. Now, so what we have obtained from using MDDs and also the strain gauges are load and the transient displacement time history. If you look at this plot, this is the Upland Street, and the measurement was taken in July 1st, 2014. This is right before any remedial measure applied on this location. As you see, this is the layer 1 transient deformations. As you see, there is a significant difference between near bridge transient deformation for layer 1 and the open track location. Layer 1 in near bridge, we almost obtained 7 millimeter deformations, while in open track location we have like 0.5 millimeter. The other thing important in here is to realize there are some negative displacement observed, like they look small compared to 7 millimeter, like 1 millimeter for the near bridge location, but later we are going to discuss those later on. They have actually important observation related to near bridge locations. This happens due to tile lifting simply. Again, remember, we installed the first MDDs inside the tie, so any lifting occur on this layer will be registered as the negative displacement. When we look at the accumulation of the intermediate layers, by intermediate layers, I mean layer 2 plus 3 plus 4. We did this for comparison purposes. We see in open track location for intermediate layer, we actually have little higher deformations than near bridge location. But when we compare them, this is the scale of 1. So, and this is around 1 millimeter and 0.8 millimeter. So the differences are not significant. And also for layer 5, which is the deepest layer, we see again we have small deformations compared to what we observed in the layer 1, and in open track location displayed again slightly higher deformations than near bridge location. Okay, this is another measurement location, Madison Street, and this time again we again see higher deformations for the layer 1 in near bridge locations. Again, 2 millimeter, around 2 millimeter, but for the open track location we have 1 millimeter. But the significant thing in this plot is to see the negative displacement is around 3.5 millimeter, which is the tile lifting. There is a significant tile lifting for near bridge locations, like around 3.5 millimeter. But again, we do not observe that in open track location. Again, for intermediate layers, this time actually near bridge locations had higher deformations than open track locations compared to Upland. Again, layer 5 deformations. So when we analyze this plot, we immediately see that the problem was in the ballast movement, which is the layer 1 deformation, as well as the tie movement. So we summarize say like contribution of the layer 1 deformation to the all total deformation in percentage, and we realize that around more than 50% of deformations occur layer 1, and actually in Upland case, they are significantly higher than OpenTrack locations as a contribution. In Madison, they are again both over 50%, except for August 2012 measurements. We have higher percentage of deformations occurring in near-bridge location. So we have these displacement time histories, and we like to calculate accelerations using those. We can do that. We have done that using sixth-order finite difference equations. This simply illustrates the time history we have. If we want to obtain acceleration in this location for this point, we use 3 points before and 3 points after. Those are displacement, and those delta t is the time step. We use this equation using this data point and obtain acceleration. Now, this specific equation has a disadvantage of losing 3 points at the beginning and the end of the displacement time history, but again, we use a sample and frequency of 2000, and we start the measurements before train hits the instrumentation and leave location and stop it after it leaves. So it wasn't actually a very disadvantageous thing. So it was quite negligible. So we have done this without doing any filter, and we obtain those accelerations. I mean, the first thing you see here is when you look at these accelerations, I mean, how do you, there are a lot of information there. It is really hard to analyze this. And the reason is that since we have a sampling frequency of 2000 Hertz, we have information in displacement time history from 0 Hertz to 1000 Hertz. So we need to choose a filter that will give us what we focus on this project. This, again, this displacement time history includes information of, like, to give an example, not just what we interested in, but like rail surface roughness, wheel problems on the train, and the train suspension problems alike, which we were not interested. So what kind of filter we should use? To decide on that, we have looked at the train geometry, and we have seen that minimum axle distance actually occurred in a locomotive. It is around 2,800 millimeter. The train speed is 110 miles per hour, which is 49,000 millimeter per second. If we calculated this frequency of this occurrence, we have like 17.3 Hertz. So we have chosen a filter that basically keep content below 20 Hertz but eliminates everything above 20 Hertz. And this was actually at first was scary, because that means we are keeping 2% of the displacement data and eliminating 98% of the data. And again, I should highlight that we applied the filter, not the computed acceleration, but the computed displacement time history. So what we have done then, we applied two filters. First, a low pass filter, that keep content below 20 Hertz intact, but eliminate the content above 20 Hertz, and this axis actually goes to 1000 Hertz. Then later we applied a high pass filter that actually eliminates content below 20 Hertz, but keep contents above 20 Hertz. Those are the displacement time histories. As you see, we have non-filtered data and the filtered data, and the results look similar. I mean, they overlap with the non-filtered data. There are not much change in the trend. But when you look at the high-pass filter, this is the information that in the displacement time history for the above 20 Hertz. So in terms of displacement, actually the significant amount of content lies on below 20 Hertz. So we can use this filter confidently. This is the verification or validation of the equation we use, acceleration, to compute accelerations. But to do that, we use another different LVDT or instrumentation. This is a simple metal plate, and it is anchored to 2 feet ground, which is 12 inches, which is the ballast thickness. And it is bind onto cross tie. As you cross tie moves, this bends, and from there we can calculate the vertical deformation. And we also have accelerometer near that instrumentation. What we have done is we have first calculated displacements. Then from this displacement, we have computed we filtered displacement. Then we have computed accelerations, and we get the accelerations from accelerometers directly, and we filter that using the same filter. And when you look at the results, we have the same trend, but we have a slightly less peaks for the computed accelerations. And the reason of that can be explained because this instrumentation simply measures 2 feet ground movement, while accelerometer measures all the ground movement, including the time. Now, since we have seen the problem for the layer 1 and the near bridge, I'm going to just show the acceleration time histories and analysis for this location. As we see, this is the displacement time history, and this is the acceleration time history. We see the peaks occur, peak accelerations occurs where negative displacement occurs, right? And if we zoom this in that portion of the plot, we see that this is like the time it starts, the negative displacement starts, and this is the time that actually the acceleration starts to peak. Now, what is this corresponding distance? When we calculate this distance, this is around 5.8 meters with the using the train speed. So basically what happens is when this wheel first compress the rail or the truck, then it travels through it, and when it hits the bridge and starts to move on the bridge, we have this jump on the rail. Due to relaxation, it first starts to tries to obtain its original position, but during that time it gains an acceleration and continues to move upward. And you can even see this after the last wheel left. Actually, this is the 32nd axle of the wheel, and we can even see that jump after the last wheel leaves. This was the Upland location, but no, this time we did not see the peak accelerations, peaks where negative displacement occurs, although there are significant accelerations in that. But we have seen those with the adjacent bogies. What I mean by adjacent bogies is those, for example, for a train car, the rail axle of that train car leaves, the first axle of the next car comes, starts to travel through instrument location. We call those two axle adjacent axle or adjacent bogies. So the peak accelerations actually occurred on the adjacent bogies, and we can see those in those zoom plots. And when we calculate the frequency between those point and this point, it is around 8 Hertz. Now, when we use fast Fourier transform and convert those from time history to frequency domain, time domain to frequency domain, and I should highlight that these plots are the second y-axis in here is scaled by using the obtained maximum from the near bridge location and keeping them same and scaling those the second axis to compare both figures, because it was nearly impossible to put them in the same figure and to compare them, because those are open track locations are significantly lower than near bridge location. We see as the trend for open track location, the peaks was observed between 15 to 17 Hertz, which corresponds to axle spacing. But for the near bridge location, we see the peaks has been obtained between 7 Hertz to 13 Hertz. Again, remember, we have a 12 feet distance for the bridge, so this corresponds to, this falls into domain for this location. So we can see that from the acceleration frequency domain, we have significant contribution from due to bridge than open track location. Same thing for the upland, but in this case, open track location acceleration were significantly higher. Like in the previous case, it was the peaks were 1 to 0.25, but in this case, we have like 1 to 0.054. So we observed a similar trend as the previous case. Now, we realized that this is the main problem is the tie gaps due to differential settlement. The main problem is the tie gap. So the remedial measures we applied should fix that problem. We have used 3 remedial measures: polyurethane injection, under tie pads, and stone blowing. We call polyurethane injection or chemical grouting were applied the previously instrumented upland location. Stone blowing was applied the previously instrumented Madison street bridge. And we have instrumented a new location that we did not have previous information, which was under tie pads. It was still on the Upland street bridge, but it was at the other side of the bridge and on a different track. This is like 4 parallel track. Now, when we look at the polyurethane injection, what was the point of doing polyurethane injection is we hope that we can insert those tubes. Then we can put 2 component polyurethane inside those tubes. And how this polyurethane works is it has 2 components, and when they mix, they immediately starts to expand. So it becomes a foam. So we were hoping to fill under tie with that foam structure with the polyurethane. And when we installed that, we realized we had a lot of trouble to actually inject those polyurethane inside this tube, because there were the track was significantly degraded. There were a lot of foul material. So we can actually see that glue is coming out as the foam as we install them, as we insert them inside. This is the permanent deformation trend. We can also obtain permanent deformation, permanent settlement using MDD information. This is from the beginning of the project to September 2015. Again, those lifts correspond to tamping, which is the geometric correction of the track at the time. We see that after when we apply the chemical grouting, we lifted the track significantly, and then later on it slightly started to decrease, then picked up decreasing, and it gained its original position. Now, when we look at the time histories, both in displacement time history and acceleration time history, we see that at the beginning, immediately after we inserted the polyurethane injection in 17 July, but take the measurement in 22nd July, we have a very little displacements, and the accelerations are small too. But in January, we see that displacement starts to increase, which is around 3 millimeters now, but there were still no negative displacement on the track. But in May, we start to see that negative displacement, which is the tile lifting that we observed before. And again, when you look at the acceleration time history this time, you can see that peaks happens where the negative displacement occurs. And this is the zoomed in display to see when the negative displacement starts to occur and when the acceleration starts to peak. And I should highlight that this, remember, for the upland, the negative displacements and the accelerations peaks were occurring between adjacent bogies. This now with that new profile, it showed similar trend to Madison. Now, we also applied storm blowing. The purpose of storm blowing was this time by using smaller particles, which was ½ inch to 3/4 inch particles. We lift the truck, we lift the tie, and we insert smaller particles under tie. So we fill that gap with the smaller particles to supply a new support. And you can see the permanent settlement behavior. There were problems with the LVDT, so we had to reset them, but you can see what happens after storm blowing. We lifted the truck, and you can see the deformation behavior. Like, it doesn't deform a lot. But now, when we look at the time histories this time, those are all, again, near bridge. We do not see January, we do not see significant deformations. In May, we do not see significant deformations. There is no significant negative displacement. There are some, but they are not significant, around 0.5 millimeter. And those are the accelerations less than 0.5 G. So basically, we can say like storm blowing work in terms of supplying support under ties to prevent lifting excessive dynamic loss. Under tie pad location, under tie pad installation, what we have done in here, those ties include under tie pad already installed. Basically, they are the elastic pad glued under the tie, and we replaced the 30 ties from bridge as a block of ties and placed the under tie pads in this location. But again, we did not have multi-depth deflectometers in this location, but we have used a different instrumentation to calculate the transient deformation. As you see, again, with the under tie pad installation, we do not have a significant vertical deformation as well as no negative displacements. And the accelerations, again, when we compute the accelerations, they were small. And again, when we convert transfer those accelerations from time domain, the frequency domain, we have seen a good trend, which is the axial spacing frequencies display higher peaks than the bridge distance. With that, I'd like to conclude those 3 points, which is the ballast layer is the primary source of the transient deformations near bridge locations. Negative displacement observed near bridge locations caused by unsupported ties, which was the main problem of bridge approach problems. And remedial measures to supply lacking support to unsupported ties remediate the problems observed, such as storm blowing. And I'd like to acknowledge everyone who involved in this project. And with that, thanks. I can take any question now. Go ahead.
I have 2 questions. Okay. The first one is, if I was wondering if the temperature has any influence on the measurements, and if so, how do you consider them? And the other one is, why to measure displacement to calculate why to measure displacements to calculate accelerations instead of measure acceleration to integrate and find the displacements? Okay.
For your first questions, when you ask about temperature, do you mean do they influence the instrumentation or the displacement? Displacement behavior.
The displacement behavior.
Okay. For the displacement behavior, we started in August 2012, and we have measured through 2 years, and we have measured August, September, January, and May. So we have covered all the climate conditions for this, or temperature conditions for this specific truck, and behavior were mostly similar, but in January, due to stiffening, we have smaller deformations on both in the ballast layer as well as in this under intermediate and layer 5. For the accelerometer condition, when you integrate from accelerations to displacement, you lose a lot of things. I mean, basically differentiation from displacement to accelerations are, I can say, more numerically correct than integrating from acceleration to displacement. Usually, even like companies, like those FWD companies, if they are calculating displacements directly, they advertise through saying like, we calculate displacement, we do not calculate velocity or accelerations. So this was one of the things regarding that. And for the calculation of acceleration, when you use accelerometers, you put this on top of the tie, right? You only calculate the accelerometer for the behavior of the tie, and you assume ground as full. You do not divide it into 5 layers. So this was another reason why we use displacement instead of accelerometers. So do you have another comment?
No, I guess. No, I understand the second part, but the first part, I don't know if numerically it's more reliable to calculate area under the curve than slopes in the cloud of points that is not following a smooth path.
For the first part, you mean?
Yeah, I feel like it's more accurate to calculate area under the curve numerically rather than the slope, because if you have if you have certain degree of noise, the slope is going to change every time, but the area is more like the fact that you have noise is not going to affect the area under the curve that much as if you have a bunch of slopes one after the other.
Okay, but answer that this way.
This was one of the reasons that bunch of slope was one of the reasons we applied a filter, because remember, as I showed, it was really affecting the acceleration behavior significantly. But also remember, we have a very small time step, like 2000 hertz sampling frequency corresponds to like 0.0005 seconds. So that slopes, that the time scale we correspond, like we are looking at the 2000 points in every second, actually too small to say like made significant difference in the results.
Yeah, maybe we can discuss after, but
okay.
But if you find the area under the curve, you don't need to filter as much as if you're working with the slope. But I understand the other reason, like if you have the accelerometer, you just have it on the surface, you don't have the whole profile through the depth of the, I think that's a stronger reason.
Displacement, transient displacement. Under the train, every wheel of the train, you have everything.
Mm-hmm.
If it's just accelerometers, the way you interpret from the vibration trends, what's going on, where, in what track substructure layer, it's totally unknown, okay? You're fishing. And very much the way accelerations are interpreted from accelerometers depended on filtering techniques, and the right technique, if not applied, you'll get totally different results. It's just like the constant in integration, that you never know what that constant is, right?
Mm-hmm.
If you have displacements, you have everything crystal clear. Actually, that's what we did. We used one of the ballast deformations with one LVDT measured, and that's how the 30 track tie or 30 tie track panel case, we were able to check accelerometer readings with the way we did filtering for results with actually the LVDT installed displacement measurements and the accelerations based on that. So using the same concept, then we were able to do all the other MDD results, you know.
So if we have used acceleration
Directly at the first, we wouldn't be confident to use 20 hertz filter because we will not have this plot in displacement. You could, I mean, in here we can see like actually the content is below 20 hertz. With accelerations, if we apply this filter, the direct accelerations, we were gonna reduce significantly, and we were not gonna see confidently what's happening. Actually, what is the important content that we are interested in? This is another point.
A follow-up question. Because geophones and accelerometers are commonly used when you really want to monitor high, let's say, frequency movements. And this is earthquake instrumentation, FWD as well, because we really apply an instant pulse loading. I think there must be a reason why people have been using geophones or accelerometers. One of the things that I'm thinking about is in LVDTs, because in the high-speed measurements, are you using LVDT with a spring?
No spring. Well, they're not spring loaded.
Huh?
They're not spring loaded. You don't have the luxury to be able to install MDDs every location you want actual, dynamic responses, right? That's going to be so costly, almost impossible. Accelerometers really help that, any anomalies and things. If you stick with the way that you filter and analyze the accelerometer data. So that's what people are doing. But then, depending on the different dynamic loading trend, different train loads and things, extra spacing, like he mentioned, some of the filtering techniques may cause missing data that you may not be seeing the full picture value. If you have displacements, though, I mean, that's where we started from the beginning. Which layer is contributing to any differential settlement at bridge approach, right? What's causing the bump? Now you have all the layers, dynamic, transient responses directly to be able to see that.
I was saying, so that's I think very good information, but the LVDTs, as far as I know, because they have their inertial resistance and damping, whether you use spring loading, anything else. That's why I think for high speed, especially high frequency responses, are they do you think reliable enough to
If you're interested in high frequency
content, like let's say a rail vibration, like to give an example, if I like this is if that was an elastic thing, and if I move this and leave it, that was gonna vibrate, but during that vibration it was gonna vibrate actually inside of a tube. It wasn't just gonna be stiff structure that makes this behavior. So there was gonna be, in the high frequency, there was gonna be little movement inside of the structure too. If I used accelerometers, I could have captured with the high frequency of that content as well as this high deformations, like high movement, like from this point to this point. But again, you should ask the questions what I am interested in. Am I interested in the movement, this movement behavior of this large deformations, or am I interested on the behavior of the small deformations that occur in that with the small, very small time step? So.
Yeah, for our purposes, everything that you see on the power spectrum curve, we are really working with low frequencies in the case of geomaterial, ballast, sub-ballast. But again, I think you missed that one, Hussein, but you should remember, when we go back to the track panel, where actually Mike Thomas instrumented, accelerometers right there, putting different places, accelerometers, at the really high frequencies, you can see the bending modes of the ties. That's how actually some of the Railtech researchers are working now on the tie designs and things. So what kind of dynamic loading aspects, but again, that wasn't our objective. Our goal is track substructure vibrations.
Yeah, this tie here actually, it wasn't the focus of this presentation, but it had like, if I actually go into this figure, here, you see that there is a 1, 2, 3, 4, 5, 6, and there is 8 accelerometers on this tie only. And they are installed on rail too, as well as the different locations of the tie. So, but again, this wasn't to investigate the transient deformation. This was to investigate the bending of the tie.
Is there any effect of moisture in what you're measuring?
Moisture in the
yeah.
displacement?
Yeah, in the track structure, for example, your substructure.
I mean, we haven't, in the substructure, we have measured displacement again in 4 climates, but we haven't specifically looked at issue what moisture does to the substructure.
It's a certain set of data affected by high moisture in the springtime, though, right?
Yeah, and January with the freeze conditions, we have smaller deformations, and spring we have higher deformations, but we did not specifically focus on that. So. Any more questions?
How about the natural frequency of the system? Are there any issues being closer to that, or when they design this entire structure?
When you say
Natural frequency, what do you mean? Do you mean like
Resonant frequency, for example, the high frequency passing of the cars.
yeah, again, we
issue? Which is because the train speed is 110 miles per hour. Do you mean like there is an issue with the railway velocity problem, but we were not reaching the railway velocity in this track because 110 miles per hour is still not that high. Right?
But will this be an issue with the maybe high speeds?
Yeah. Yeah. This is another research topic. In Europe, especially when they hit really high speed, they now need to look at the railway velocity in the ground. So.
Professor Hayvan's research.
Yeah.
Critical velocity.
Yeah, actually on that track, the train actually travels with 150 miles per hour on some portion of the track. So maybe in there you might investigate that, but not in the portion that we had.
You see, what was the big difference between AMTRAK Chester bridges and some of the dynamic trends at the bridge approach versus you also worked on instrumenting Norfolk Southern bridges, right? Freight trains. First, give us the details about what kind of loading conditions in both tracks, in both lines, and what aspects came up.
With the freight,
I haven't showed the freight train information, but with the freight train, what you have a lot of axles. Since there are like 100 cars, you have like around 400 peaks, as well as they are significant, as the wheel loads, they are significantly higher than what you have in the passenger train. But also, remember, freight train also travels with a 40, this was like 40 miles per hour compared to 110 miles per hour. And the axle spacing is different too. So what we have seen, the frequencies lay below 5 hertz. Even in the acceleration frequencies lay below 5 hertz for the freight trains. But for the accelerations lay below 20 hertz for the passenger trains. This was one of the significant differences. The other difference is the layer 1 deformations were higher, and we did not see any like negative displacement or tie jumping in the case of freight trains. So
When you go slowly, you don't see that.
no. We did not.
What was the mechanisms of this? What is it behind this?
behind the jumping,
Why don't you see that in the slow-moving train?
why I don't see that on slow moving train?
Is it the friction components, the friction between the components?
I can,
Maybe, I mean,
as one of the explanation is, as the wheel moves through, it has enough time for the instrument to tie to slowly lift up, maybe, to come to its original positions. But with this higher speed, basically you hit the tie, you bounce the tie in the ground, then you leave it immediately, then it starts to gain an accelerations to keep its position, then it jumps. But in the slower train, you basically leave it slowly, then it can get to its original position. This is one of the explanations that I can have about it.
Did you have any higher frequency vibration trends seen in any of the Norfolk Southern ones?
Yeah. In terms of, when you say higher frequencies, do you mean in the accelerations?
Right. When the train, freight trains at 25 miles, 40.5 miles per hour coming and entering the bridge versus 110-mile train coming and entering the bridge in the case of AMTRAK. AMTRAK 1, we concluded that train speed has created some of those negative displacements due to the nature of the waves hitting the rigid abutment, bouncing back and creating the tides, up and down motion, and this is all the higher frequency dynamic response trends that we don't see ever in Norfolk Southern case.
Yeah.
So this is really interesting, guys. What happens is, I know he's supposed to tell me about this, but the tie, as the tie is being loaded, okay, it just jumps up, as it heaves, he showed the heaving. As it goes up, now it hits harder down, as the next wheel comes and pushes it down, right? So as that impact load is acting on the ballast underneath the tie, concrete tie, it's creating in very short time a huge gap, crushing aggregates, ballast particles, as well as increasing the gap size, and this is all an effect of the speed. That didn't happen in Norfolk Southern.
Actually, one of the things is they usually, when they list the problems in the literature that it is on the near bridge locations of for which approach locations is like component breakages, like even broken rails, broken ties, mud pumping, degraded aggregates, those even like broken fasteners, those are all explained that this impact loading or impact hit of the tie to the ground and basically moving upwards immediately.
All right, any other questions? Any other comments? Professor Tutumlar, you want to make?
Sometimes I talk too much.
We because he finished early, so we maybe filled that time with some interesting questions. I think.
Okay, that's good.
Yeah.
One of the things that really work very well is storm blowing application, and this is we didn't expect this to work that well, and I don't know if Hussein can comment on that. What's going on in storm blowing and why? Here's the thing: how it worked and why it worked. Well, let's get Hussein on why it worked. But facts. Every 3 months, they used to have this gap opening in those instrumented ties at the bridge approach. And then after storm blowing for 12 months, almost a year, there wasn't much of tamping or maintenance needs. It used to happen every 3 months. I was just talking to actually one of the AMTRAK people yesterday. He was amazed at how storm blowing being an old approach, primarily used in UK and Europe, not much here, but they have even huge equipment to do that kind of maintenance activity in Europe, but not here again. It is something we so clearly help because of what? Or what?
Because of this. Let's say this is the original position of the rail, right? And there is a gap underneath, and we have ties like that near bridge, like let's say 6 or 7 ties on near bridge locations like that, and the distance between those ties 2 feet. Now, when the wheel hits that, it basically deforms this rail, leaves it, and this rail wanna go to its original position and gain a momentum, gain an acceleration doing that, and it jumps. Now, if I fill that with smaller particles, right, for the 6 or 7 ties in this location, now I have a real position in here. Now, when I displace, when I hit that location with the wheel, now it's gonna displace, but it is not gonna have a lot of to go up because the displacement is gonna be smaller than the gap that it's gonna gain its original position. So this storm blowing actually kind of prevented this jumping up thing. And at first I was struggling to think, why would storm blowing prevent a negative jump? Because what I was thinking, that does not restrain the rail to go upward, right? It's basically supply and support under the tie. But then later realized the lack of support under the tie, that gap, that tie going down and leaving the tie immediately, and the tie wanna gain to its location, and this jumping up was the problem. So storm blowing by inserting smaller particles underneath the tie solved this problem.
Why is not breaking any more rocks?
There's better load distribution under it too. Because those are smaller particles.
Less stress on the rocks, there's less breakage, and it keeps going like that for a longer time.
Yeah. Those particles, like for ballast particles, they are around 2 inches in size, but those particles are 0.5 inches size. Again, why we use this gradation is for railroads, drainage is important. We use uniform graded aggregates and large aggregates. But again, with that, it comes with the larger force distribution on each aggregate. But if I put this here, the smaller aggregates, now I can distribute the loads under the tide better to be basically the neighboring large aggregates.
Is there any way to prevent it before it happens? Is there any way to prevent it before it happens?
Before what happens?
Before we install
Lifting happens? Like preventing the gap?
So we see the gap and then you still below it, right?
Yeah.
Is there any way to prevent it? Like,
Prevent the gap?
When you like build the railroad tracks, do this.
Yeah.
Can we design with this in mind?
Okay, here's the answer to that. I mean, yeah, you can make bridge flexible, I believe. If you
I think he's asking this.
yeah, prevent the gap, you mean?
Yeah, you say that the stone line helps it.
There are you can make a in the design perspective we haven't investigated those, but you can make a smoother transition, making different gradations. This is one solution you can apply. You can use under tie pads or elastic tie pads as we
What's
have
the mechanism
discussed.
there? Are they related?
The under tie pads. The under tie pads, the mechanism in under tie pads, basically you apply better load distributions under the tie as well as an elastic support, like you incorporate the damping in there with that elastic material to basically to reduce the impact on the particles. To the other thing you can do, you can increase the lateral resistance of the ballast layer, so that because when ballast displays, actually it usually displays laterally. By laterally, I mean it moves not in the vertical permanent vertical direction, but the lateral direction. You can increase that with the basically reinforcing shoulder, or you can use jaw grids to increase the lateral resistance. Those are the design approaches could be investigated on those locations. But again, we haven't done those. It wasn't in there.
It wasn't.
It,
Why didn't they install a geogrid?
it's your political thing. I do not know.
It's not political. No, simple answer.
Why didn't? Because in order to install it, you need to scrape down all the ballast layer, and you need to close the traffic, and you need to put. And again, it is and this is a passenger train, and it is hard to say passengers that tomorrow no train, because we are gonna put geogrids on the track.
You can't finish that work within one night. They give you 5-hour window to operate.
Yeah, we usually work during the night. Actually, all the polyurethane injections, what we leave the track at 5 a.m. And so.
Sure. So I was you didn't mention about the loading. Like you worked on one specific track, right?
Yeah.
And then like, do you have any information about the like overall loading of this track, or do you assume?
We also analyze the loading distribution to compare those between open track and layer bridge, and we have some differences in terms of percentages. When we instrumented the loading, I should go to beginning for the strain gauges. What we did. Okay. Here we.
No, but like, those are like field responses, right?
Yes.
So I was asking in terms of applied loading, and which is gonna actually lead me to another like follow-up question.
No, I just got a follow-up question. Maybe
No,
we can ask after this
like
one.
I was gonna
Yeah.
ask you about modeling, but we can talk about later.
Okay.
Because yeah, almost
That one is we have like two shear strain gauges. One on top of the tie and one on the crib side. By crib side, I mean between the ties. So we assume that with the displacement here, we assume this load is full, so we can calculate the tie support by comparing this load to this load. So we analyzed those, and we have seen some differences between near bridge location and open track location. Usually in the open track location, or where there is a good support under the tie, we did not see, we see good percentage of the tie support. But in here, if there is a void underneath, we did not see that. Or if there were like issues with the ties.
Basically, the same time that you get the displacement profile from MDD, the wheel right in between the ties there, you're actually capturing by the bending of the rail, okay, the load magnitudes on the wheels. And that's what you see on the right-hand side. The 2 locomotives on both sides and 6 passenger cars, the typical SLA express train. These are the loads measured that way. So you know the dynamic load, you know the dynamic transient deformation, as well as permanent deformation.
All right, that concludes our CAN seminar this week. So let's thank Hussein for this nice presentation and the